Good afternoon, everyone. Before I get into today's lesson, I'm just going to go and take up a question from the homework from a couple of days ago. So this is number 16a. Okay, and it's basically asking us to do a little curve sketch. Okay, I've got x over x squared minus 1. Okay, and I'm going to move through this fairly quickly because I know you're all diligent people who have all done the homework already. So you should just be able to follow along as we go through. Okay. Key features we need. First is the vertical asymptotes. Okay. Where do I find vertical asymptotes? Those are the roots from my denominator. So I'll take a minute and factor there. It's a difference of squares. So x minus 1, x plus 1. Okay. And so my vertical asymptotes are at x equals plus or minus 1. So I'm going to have two of those. Okay. Other things I can pick off quickly. I'm going to come back to the asymptote in a moment for horizontal. Okay, but our x-intercept, that's the root from the numerator. Okay, so we just have a single x there, so that would be 0, which means that our y-intercept is also going to be 0. Okay, right to the horizontal asymptote. Okay, what's going on here? Okay, we haven't really directly talked about what happens if the power is larger in the denominator. Okay, but one thing we can do is that infinity test thing that was mentioned in the video on Tuesday. Okay, so here's how it kind of works, right? If I want to see what's happening at end behavior, okay, I would plug in infinity, okay, and see what happens. So at the moment, I would have, that would be infinity over infinity squared minus 1. Okay, from the table of rules we had, that's infinity over infinity, and that's indeterminate. Okay, we don't really know what's happening there. Okay, so to get around that, what we're going to do in our function, okay, is divide top and bottom by x. Okay, so I take everything in my original expression here, okay, and I'm going to divide it by x. So on the side here, we'll write that down. So on the top, I would have x divided by x, which is 1. In the bottom, I have x squared divided by x, which is x. And then I have 1 divided by x. Okay. Now I try plugging in infinity. Okay, that's just a different way of writing my function. Okay, because I divided top and bottom by the same thing. So now I get 1 over infinity minus 1 over infinity there. Okay, from our rules, 1 over infinity would be 0. So infinity minus 0. So now I have 1 over infinity, which again is 0. Okay. So what this is saying is that in the long run, this function approaches 0. Okay. That means my horizontal asymptote must be 0. Okay. Another way you can think about that is just by comparing the powers. Okay. If you look at x squared and x, okay, and think about what's going on for a second. Right? As the numbers get really, really, really big, right, as we go towards infinity, sort of like thousands, millions, billions, okay, what happens to those two things? Okay, right, so if x is 1,000, well, x squared in the denominator is 1,000 squared, which is a million. Okay, it's way, way larger than the numerator, so that means you're going to get a pretty small value. Okay, so as x gets larger and larger, the denominator is going to get, large way, way faster than x does, and therefore it would tend towards 0. Okay, it's going to overpower it in terms of the division. Okay, all right, so there's my key information. So now let's try to put this thing together. So I'll sketch an axis. Okay, I've got asymptotes at plus and minus 1, so something like this. Okay, now here's the weird thing, right? We said our horizontal asymptote is 0. What's that line? Okay, but then our x and y intercepts are also 0. Okay, so that kind of looks like I've got a point on the asymptote. But I think I mentioned this at the start of the unit. Okay, that's okay. Okay, we can actually pass through the horizontal asymptote and things are still okay. We just know at the end behavior, right, when x gets really large, it has to follow the asymptote after that. Okay, so at the moment, it doesn't look like we have a lot to go on here. I've got that single point in the middle, and not a lot for any of my intervals. Okay, so really, we're going to have to test asymptote behavior. Okay, do a little bit of checking and see what goes on. Okay, so without spending too much time on it, okay, to give you an example, for say this section of the graph here on the far left, okay, I would need to take a minute and do a test value of some kind. So let's say we do, -2 or -1.5, something like that. Okay, f of -2, which is below our asymptote. Okay, and I've got -2 over, using the original function, I would have -2 squared minus 1. Okay, so I have -2 over 5. That is that's a negative value. So I'm going to be below here. Okay, so most likely what is happening in that section of the graph is I have something like this. Okay, and if we do a bunch more tests, we're going to find that my asymptote behaviors are here and here and here. Okay, so what that means for this function, okay, is it must kind of look like a cubic in the middle there. Okay, it comes down, passes through, and continues. And on this end, it looks like that. Okay. So, and that's how you use those key pieces of information: the asymptotes, okay, the intercepts, and if necessary, right, your behaviors, right, doing some test values around your asymptotes to figure out where the graph is going. And that's how it works. Okay. So let's get into today's lesson. Now we've done tons of stuff with graphing. We're going to talk a little bit about modeling. So we're going to bring this back to some, again, questions that kind of go back to grade 9 a little bit here. Okay. So example 1, a rectangular garden with an area of 20 square meters. Determine an equation that models the width as a function of the length. Okay. And then sketch the graph of the function and comment on its shape. Okay, so the only thing we have to go on here is basically the formula for area. Okay, so area equals length times width. Okay, our area is 20. Okay, and I said I wanted width as a function of length, so I'm going to isolate width by dividing by L. Okay, so 20 over L equals width. Okay, so therefore my function is 20 divided by L. Okay, now let's sketch its graph. So again, we'll look at those key things. Okay, what is my vertical asymptote? Well, that's my roots from the denominator. Okay, I just have an L there, so my vertical asymptote is at 0 because I can't divide by 0. Okay, what is my horizontal asymptote? Okay, well, again, if I think about what happens as L gets really, really large, okay, you're going to have 20, a constant, divided by a very big number. For this idea of substituting infinity, right? I'm just going to have 20 over infinity. Well, that goes to 0. So my horizontal asymptote is also 0. Okay, x-intercepts. Well, actually, I should call it the L-intercept, I guess, because we're using L and W here. Okay, well, there are no variables in the numerator, so I can't produce a 0. It doesn't exist. Okay, and for the W-intercept, right, which is replacing Y here, I have length and width. If I plug in 0 for the length, it's undefined. Okay, don't actually have that. Right, So kind of like the one we just looked at a moment ago, all I really got to go on here is my asymptotes are basically the axes. That's it. Okay, well, this is really your basic reciprocal function, just stretched by a factor of 20. Okay, so it looks something like this. Okay, right, because when L is positive, the width is positive. When L is negative, width is negative, although we know those rectangles don't really exist. Okay, but there you go. Okay, so this number's coming in its shape. Okay, and we kind of already know this, right? When you look at this, as the length increases, right, your length gets bigger and bigger and bigger, your width is going to decrease. Okay, it never really reaches zero. Okay, that's the funny thing here. Like you can have a rectangle with length of 2,000. Okay, it just means the width is 1/100th, right? It's an insanely thin but long rectangle. Okay, so this is just reinforcing that idea that as length increases, W decreases, and approaches 0. Okay, again, never really reaches 0. Just technically, you could have length of 20 million and length and width of a millionth. Okay, so it never goes all the way to 0, but it does get incredibly close to 0. Right, example 2. Same idea. Okay, let's make the perimeter as a function of the length. Okay. So we'll start with our equation for perimeter. The perimeter is 2 lengths plus 2 widths of a rectangle. Now, all this, there's a length. Okay, but in our last example, we found an expression for length. So my perimeter is equal to 2 lengths plus 2 times 20 over the length. Okay, so we've got 2L plus 40 over L. Now, to give us a little bit of context, or to help us use the skills we already have, let's get it all into one fraction there. So we get a common denominator, which is L. So we have 2L squared over L plus 40 over L. So that means my equation for perimeter is going to be 2L squared plus 40 all over L. Okay, let's do the same kind of analysis. Sorry for that little bounce there with the graph. Okay, and see what's going on here. So our vertical asymptote. Okay, once again, that's the roots of the denominator. So we're going to have 0. Okay, horizontal. This will not have a horizontal asymptote because the degree of the numerator is 1 more than the degree of the denominator. This is going to have an oblique asymptote. Okay, so on the side here somewhere, we're going to have to do a little bit of division. Okay, although there's really not a lot to do here. I've got L divided into 2L squared plus 40. Okay, so let's see. I multiply by 2L squared. There's no second term, and I just get plus 40, and I'm done. Okay, so my oblique asymptote, okay, would be y equals 2x or p equals 2L. So this is p equals 2L. L. Okay. X-intercept. Okay, we would try to find roots of the numerator. Unfortunately, once again, there aren't any, right? It's a sum of squares. Okay, so I don't have any roots, at least no real roots. So there is none. Okay, and again with the y-intercept, there isn't one of those either. Okay, because if I plug in 0, my denominator is 0. Okay. So again, not a huge amount to go on. It'll be enough to get a rough sketch of what's going on here. Okay, so vertical asymptote is at 0. So once again, the axis is the vertical asymptote. Okay, my oblique is 2L. So that would be a line with a slope of 2. So let's see what we can do here. And that looks something like this. Okay, that's it. Okay, but again, we'll use a few clues here. Because this didn't have any intercepts, okay, my graph can't possibly cross the axis, right? It doesn't touch the x-axis at all. So that means the only places I could put these curves are up here, okay, and down here. So my graph would look something like that. Okay. Again, we're going to briefly comment on the shape here. So what's potentially interesting here is that, again, if we focus on the positive part of the graph, right, because the negative values for length and width can't really happen, we have something that's kind of like a parabola. Okay, and there's a lowest point, so there's a minimum in there. There's a minimum possible perimeter. Okay, and you may recall from grade 9 that would be when a square occurs. Okay, there's going to be a minimum. Okay, other things, right? As we go off to infinity here, it approaches 2 lengths, right? Okay, and that should hopefully make sense, right? We talked about the idea it would be an incredibly thin rectangle if you're starting to stretch this out, right, from that previous slide there. So then my perimeter would essentially just become twice the length, okay, because the width is almost non-existent, okay, as you keep going off to infinity there. Okay. Just a brief comment, there is a minimum perimeter. Let's see how bad my writing is here. Hey, there you go, not bad. Okay, and that occurs, and there's a square. Okay. Okay, final example. A little bit different. All right, length of time it takes to complete a jigsaw puzzle is inversely proportional to the number of people who are working on it. Okay. If it takes 60 minutes for 2 people to complete the puzzle, determine how many people it would take, theoretically, to finish the puzzle in 10 minutes. Okay, so a couple things to deal with here. The first is inversely proportional. Okay, so just to give you what that means, okay, if 2 things are proportional, okay, and this is going back again to like grade 8, grade 9, like direct variation, those kind of things. Okay, so if it's proportional, okay, that means the relationship looks something like this: y equals k times x, right? They move up together, okay, by some kind of a multiplier. If they are inversely proportional, Okay, that means that y is proportional to the inverse of x, okay, or really the reciprocal of x. So the general structure of the equation is something like this: a constant divided by x. Okay? That's what it means. Okay, so if it's inversely proportional to something, it's y is a multiple of a constant divided by x. Okay, so y is a constant divided by x. Okay, so let's put that to work here. Okay, we have the number of people and the time it takes to finish the puzzle. Okay, so again, if we use some variables that may make a little more sense in the situation, right? The time it takes to finish the puzzle is some constant divided by the number of people. Okay, let's use n for number while working on the puzzle. Okay, so this is time, number of people. So our first goal is to figure out what the constant is. Okay, but fortunately, we have the other two pieces of information. Okay, we're saying it takes 60 minutes for 2 people to finish the puzzle. All right, so just quickly rearranging there. That means 120 is equal to k. Okay, so my constant here is 120. So my equation that links the two things together now, okay, is going to be t equals 120 divided by whatever number of people there are. Okay, we want to finish the puzzle in 10 minutes. So that would mean 10 is equal to 120 over n. Okay, we switch it around, multiply n up, and divide the 10 down. So what this is saying is, in theory, okay, if you had 12 people working on this puzzle at once, you could somehow finish it in 10 minutes. I'm guessing those 12 people would be linked telepathically or something to be that efficient. I think it's more likely to get in each other's way. Okay, so obviously that's a bit of a silly example, but that's how the structure of inverse proportionality works. Okay, it's a constant divided by the other variable. Okay, so there's an intro starting to work with some rational models. Okay, for practice, this little hodgepodge, it's coming from different sections of the textbook, but there's only a total of 8 questions there. Okay, so page 155, 10 to 13, and so on down the line there. Okay, thank you very much for watching, and I will see you tomorrow.